My name is Greg Kaiser, and this is Think Supersystemic. We explore the science, art, and economy of interconnectedness. Today, our guest is Dr. Ricard Sole from the University of Pompeu Fabra in Barcelona. Dr. Sole heads up the Complex Systems Lab at the university. His work in understanding how complex systems, such as economies and forests and immune systems, how they actually work, is, in my opinion, some of the most important work happening in science today. Hi, Ricard. Welcome to Think Supersystemic.
Hello.
Thanks so much for agreeing to be on the show. I find your work with complex systems is incredibly interesting to me for many reasons. But to get us started, can you I know complex systems can involve quite a wide range of topics and areas and so forth, but can you just give an overview of your work, kind of how you got into studying complex systems, and what's the breadth of your work now?
Sure. Yeah. I mean, the historic thing is, I always wanted to be a biologist when I was a kid, or a naturalist. I wasn't sure. But then I had this physics professor, teacher, sorry, when I was very close to go to the college, and I became fascinated by physics, and so I decided to do both bachelor degrees. And then I was more and more involved into that because I was really motivated for what at the time was called theoretical biology, and then at some point I met Brian Goodwin at the Open University, who was my supervisor for a while, and then Stuart Kaufman, and I was aware about it. So I became interested in what at the time was called theoretical biology. Almost no one knew about that, but the thing was that there was this connection between mathematics and biology, which I found fascinating. And years after I met Brian Goodwin at the Open University, who was a former PhD student of Waddington, and it kind of opened my mind to many things of how to relook at biology. Then Stuart Kaufman came into his office one day, and eventually he invited me to go to the Santa Fe Institute. And my main areas of research have been changing over time, but essentially all the time I go around trying to find out whether there are fundamental laws of complexity, of biological complexity in particular.
Okay.
And that's a little bit my big research area.
Okay, cool. So can you give an overview of just, I guess kind of the discipline in general of like, what is a complex system, or what are some examples of complex systems, just so we can kind of get the bigger picture?
Yeah, that's an issue because there's a discussion about what exactly is complexity. But I think that we all more or less agree that it has to do with the presence of emergent phenomena. So in other words, that you have a system made by many elements, and that the interaction between elements, and sometimes interactions are much more important than the elements themselves, creates new kinds of phenomena that you cannot reduce to the behavior of the components. And an ant colony or a termite nest, I think that's the best example you can actually formulate. The termites have no idea of how to build a nest. So as individuals, they are blind, they communicate with closest nest mates. But there's a collective intelligence that you cannot explain by the properties of the termites as much as you study them. So the collective is able to create a whole structure orders of magnitude larger. So that's the emergent structure which connects us with the idea of complexity.
Okay, and so for example, is an economy considered a complex system?
It is. In many ways, it's clear that the fact that the agents in the economic system do not have complete information, that information propagates in ways that pretty much resemble things you see in self-organized systems, and feeds back to the agents. That creates a number of phenomena that cannot be broken into pieces. So there is complexity there also.
Okay. And so if an ant colony and a termite colony are considered complex system, is also the greater forest that's around them that they're a part of, is that also considered a complex system? Are there emergent phenomena that come out of, say, a rainforest or a temperate forest?
Sure. Yes. Again, here the interactions are actually if you want, this is the fabric that sustains biodiversity, and that an ecosystem is healthy, is not fragile, that can cope with fluctuations, is very, very much connected with the way species interact to each other. So the web of interactions is the emergent part that clearly, again, cannot be reduced to the observation of single species or an inventory of species. You need the web.
Okay. Yeah, it's interesting. So one of the conversations I had yesterday was with a scientist who's studying the human microbiome. And so he focuses on, all the microbes and how that impacts our health and our mental state and all that stuff. So would you say also the human microbiome is also a complex system of the same order?
Yes, yes, absolutely. And it's a fascinating one. We don't know much yet. It's the result of millions of years of coevolution. And it is several levels of complexity that we have to cope with because the microbiome, for example, the gut microbiome interacts with the immune system and with the nervous system. So there's a number of layers of interactions that we don't know much about. And all this realization that we are not an organism, we are a holobiont. That we are actually kind of an ecosystem.
Interesting. So your work, you're focusing specifically on trying to identify rules that govern these different complex systems, so that you can then kind of assess the health of them or improve the health of them, that sort of thing.
You mean for ecosystems?
Yeah, for ecosystems. Like what's the end game kind of for kind of identifying the rules? Like how is that going to help improve things or yeah?
Well, on one hand, we've been working on ecological networks, and many other people. We were kind of the beginning of the network science emergence, and there's clearly a basic science part where we needed to know what's the architecture of these webs to identify potential fragilities. But right now, when we face the possibility of tipping points in a not so far future, tipping points meaning that ecosystems can just collapse completely. What we are trying to do is to using different views from theoretical ecology to synthetic biology, see how could we modify some interactions within ecosystems, particularly in drylands, which are especially endangered, and see how to modify the system to preserve biodiversity. It's a very different concept from what you could think in terms of engineering in the standard way. So what the idea is, what kind of potential things we can exploit from an ecological web, so that small modifications could guarantee that biodiversity is kept, because biodiversity is the key for really making the system strong against changes.
Okay. So do you think the equivalent, so talking about biodiversity, do you think the equivalent principle can be applied to, say, an economy? An economy generally would be better off and less likely to collapse if it had greater diversity and complexity?
Sure. I'm not an expert on that, but clearly diversification, it's always a source for, I will say, for all the systems that you can define that.
Yeah.
Is a source of robustness, right? That you're not dependent on a small amount of things that can fluctuate wildly.
Okay. Yeah, when I was speaking to the microbiologist yesterday, he indicated the same. Like one of the problems that we're finding is that people who are sick via the digestive system, the gut, is that there's a lack of diversity, and reversing that lack of diversity by boosting diversity can improve the outcomes of the health of the individual. So that's super interesting stuff. So what
yes.
what would you say are the what do you think are the upcoming promising areas of research in complex systems, not just your work, but in general, but also your work?
Um, I think there's a number of open domains that once we have the clear way of how to attack. I mean, there's several people trying to go into, for example, one of the main things that we are very fascinated of is universality. I think that very different complex systems share some really fundamental principles of organization. But to give you an example, why I think is still a gap that people starting to approach that gap, which is the following. Take language, for example. In language, we have found that if you analyze very different languages from all over the world, there are very strong regularities. Languages are very different, but they share very strong statistical laws. That could be kind of the universals that we physicists talk about usually. But then there's universals that come from universal grammars, the Chomsky's picture. There, you have something that is closer to maybe to computation, etc. But there are universals also. So it should be something in the middle that connects the two kinds of views of looking at universals. And I think that's a fundamental part of the puzzle that we haven't solved yet.
Okay.
People from different areas is approaching this, but if this is solved somehow, it could be a big thing within complexity.
Okay. So if research in complex systems continues over the next decade, 3 decades, 4 decades, do you think in 50 years we'll be at a place where we have this really deep understanding of how our world works, like, and how our economies work, how forests work, how our microbiome works, that we kind of have, it almost seems like people like you who understand complex systems, or the general practitioners of this knowledge, will need to rise up into a level of even government and that sort of thing, where we're applying these concepts to our regulations and to our incentives that we put into our economies and so forth. Does that seem like, I know that seems kind of like a fairy tale world that I'm painting, but it seems sort of like that's the direction this has to go in order for us to continue to evolve in a positive way.
Well, we'll see. I mean, when I started with this 30 some years ago, I thought, I told myself, you know, in 20 years, chaos theory and cellular automata will be taught in schools. That was clear. That was a fairy tale, really. Yeah. But with the beginning of this century, we experienced this revolution of complex networks that, in a way, has brought to many people ideas that come from really from the core of complexity. So I'll be optimistic in terms of that becoming more and more relevant. In a way, it is now that we have this big epidemic event. You have in the news a lot of discussion about, you know, mobility networks, social networks, concepts that people pretty much ignored, like how epidemics work in reality, and the fact that you have multiple scales involved. How it is going to percolate into politics, that's another issue, because very unfortunately, the political class in many places is pretty much outside the domain of science. So I think that an important effort has to be done is to bring that into the politics, because it's difficult to understand a future, as you said, in some decades, where this is not part of the decision-making processes, because we will confront big problems like climate change, and that really needs to see a systems perspective.
Interesting. Are you familiar with the work of Daniel Dennett and Susan Blackmore in terms of memetics, the study of ideas and how ideas kind of move through our, you know, the collective kind of wisdom of humanity and so forth? And I guess the second part of that question is, do you think that do ideas in the way ideas kind of take on their own life and kind of get transmitted through human societies and so forth? Would you say that's also a complex system of sorts? So an idea ecosystem or ideas? Yeah. Okay.
Absolutely. I don't think we have yet a good theory for that, because there's I completely agree. I mean, ideas, you know, propagate between humans, maybe because we have that's a speculation, but, you know, since language in a way works like a virus, the possibility that ideas infect our brains, this is a very, very interesting metaphor. I think that is essentially correct, except that we have the cognition layer. And so it's not as simple as a virus infecting cells. But yeah, I completely agree. I think that is something that is really worth exploring as a scientific idea.
Interesting. Is anybody studying that currently from a complex systems aspect that you know of?
Not that I'm aware of in terms of scientific work, as we were discussing, but there's a lot of people working on what happened in social networks, in particular in any networks of knowledge, from Wikipedia or to other systems.
Yeah.
How ideas get transferred there, how there's this kind of conflicts between different views, etc. So there's a lot of things going on that. Yeah.
Cool. Great. So so just to wrap up the conversation, is there any, if there was one piece of information or one aspect of complex systems right now that you wish everybody in the whole world understood, do you know what that would be? And maybe it's happening with coronavirus.
Yeah, tipping points.
Yeah. Tipping points. Okay.
I think tipping points are really, really essential. It's an outcome of the non-linearities of complexity. It's something that we like it or not, it's part of the future outcomes of ecosystem degradation. And tipping points are so important because they change a lot your perspective about risk. If you think that things are going to change smoothly in time, you can have the picture that, well, we will change that back somehow in the future.
Okay.
But if there are tipping points, and there are tipping points, things are going to be very different. So we need to know about that.
So tipping points might otherwise be called the point of no return in a way, like with regards to climate, for example. Like when we get to a certain temperature,
Yes.
then everything falls. So it's like a threshold that's crossed and everything changes. Okay.
Yes, and importantly, I mean, once we go beyond the tipping point, we should realize that things like our planet, for example, will experience a runaway effect. It's no technology probably going to be able to cope with it. So before that happens, we need to really do something.
Okay. And would you say that another tipping point that might be taking effect right now is with regards to our economy is if a certain percentage of people become unemployed, say 45% or 50% or 60%, then kind of we have civil unrest to such a degree that it's hard to stop. Would you say the tipping points can also apply to economies as well?
Absolutely, yes. We see more and more, political and social turmoil in many different places. And the economical system has reached a point actually where you have this huge inequality that cannot be sustained itself in the future. So that's something that I think there's a number of people thinking about pretty much. Why society is accepting that, or why society will keep accepting that in a way. And there's all the ideas that I'm afraid are pretty correct, like Naomi Klein's idea of the shock doctrine, that because we humans also have some fundamental rules of thinking and behaving, there's the potential also for authoritarian responses to that, right? Which you can see them already happening.
Yeah, for sure.
So yes, there's a complexity there. There's a complexity there that we should be able as citizens to be able to change.
Okay. Awesome. Well, this conversation was super, super interesting. And, I'm in awe of the work that you do and the Santa Fe Institute and so forth. So thanks so much for sharing these ideas today. And thanks for being on the show.
Thanks, Greg. It's been great. Thank you.
Thanks.